welcome to the course on stochastic modeling. In this lecture, we will look at an example of the hidden Markov chain model. In the last lecture, we looked at what hidden Markov chain models are, and we also formulated a method by which we can compute a probability, which we denoted as Fni, which indicates the probability that the state I is being occupied at the nth time point, along with the sequence of signals that are being emitted from the time 1 to time n, which have been observed. So we mentioned that this will form the workhorse for solving the HMM models. We will see how that happens. To illustrate the idea behind solving hidden Markov models, we will take a simple example. This is an example of a machine that is put into use in an industry. As we looked at this example in the previous lecture, this machine produces one item in every hour, and we look at the status of the item and figure out whether the item is acceptable or unacceptable, or in other words, defective. So the items being produced by the machine are the one which are the only things, the characteristics is the only thing that is observable, whether it is a defective items or the good items. In order to model how the items are being produced by the machine, we assume that the machine can be in two possible states, one being the good state, another being the bad state. As the name itself indicates, the good state is a one wherein most of the time the items produced by the machines are acceptable. Very rarely defective items are being produced. Whereas in the bad state, it starts producing defective items very frequently. And for various reasons, the machine may switch between the good state and the bad state. So this is how we are going to model the way the machine behaves. And again, through some understanding of the machine, let us say we have come up with a Markov chain model for the behavior of the machine. So the machine can be in two states, possible states, good or bad. If a machine is observed to be in a good state in a particular step, which is of duration 1 hour, then it will be in the good state in the next hour, or when the next item is manufactured, with a probability of 0.9. Else it will get into the bad state with a probability 0.1. Similarly, if the machine is in a bad state at one time step wherein it manufactures one item, in the next time step it may continue to be in the bad state with a probability 1, and therefore the probability of switching back to good state is 0. So this is a simple model that we use. We could have used some other transition probabilities also. So the state transition probabilities between the states can be written down as follows. Again, for the sake of formulating the Markov chain, we assign a random variable which stands for the state of the machine. The random variable takes a value 1 if it is in a good state, and it takes a value 2 if it is in a bad state. And therefore the probability of making a transition from 1 to 1, that is a good state to good state in unit time step, is 0.9. From a good state to the bad state, that is 1 to 2, is point 1. Remaining in the good state is what we have seen. Remaining in the bad state is P22, that is 1.0, and switching from the bad state to good state, that is 2 to 1 is 0. So that is the characterization of the Markov chain. But of course this is a hidden Markov chain because we cannot observe the state of the machine. What we can observe is only the signals. And what are the signals? Whether the item being manufactured is acceptable or defective. But if the machine is in good state, then the probability that it produces a good or an acceptable item is known to us, and therefore the probability of it producing a defective item can also be found out. So these are given to us in the sense that this, by modeling the behavior of the machine, these probabilities are also being arrived at using the domain knowledge of the machinery. So we use the number character U to stand for unacceptable item and A to stand for acceptable item. So probability that an unacceptable item will be produced when it is in a good state, that is 1, is 0.01. That is only 1% of the items are unacceptable. And therefore the probability that an acceptable item is produced when the machine is in a good state or a 1 is 0.99, or 99% of the items are acceptable. Similarly, we model it for the bad state. So in bad state it produces more unacceptable item, therefore this probability has to be larger than the corresponding probability of 1. So P of U given 2 is 0.04, that is 4% of items are defective, and 0.96% of items are acceptable in the state 2 or the bad state. Further, it is also assumed that to begin with the machine is in the good state with a probability 0.8, and therefore it is in a bad state with a probability 0.2. Then we would like to ask the following question and answer them. These are the typical questions one would be interested in asking. Okay. Further, before posing the question, we will assume that we have run the machine for 3 hours or 3 unit times, and 3 items have been manufactured, and we have noted down the nature of the items as acceptable or unacceptable. Let us say in a particular realization we have got 3 items which are of the following kind: acceptable item followed by an unacceptable item followed by an acceptable item. That is, at time 0 it is acceptable, time, okay, or we will start off with 1. At the time 1 it is acceptable, time 2 it is unacceptable, time 3 it is acceptable. So we are at the end of time 3, wherein just an unacceptable, an item, third item has been manufactured and it has been found to be an acceptable quality. With this in background, what you would be interested in at the time when the third unit time got over? So you might be interested in predicting what would be the state of the machine when the third item was produced. You cannot tell it can be very probably in being good state because we got an acceptable item. It is also possible that the machine may be in a bad state and produced the acceptable item. So we just don't know. And starting with a good or bad state at the time 1, there are many ways in which it could have evolved. It would have continued to remain in the good state, or switched between gone to a bad state in 2 and come back to the good state, and so on. You don't know. But we can only figure out what is the probability that it will be in the given state, good state or the bad state, given that 3 items that are manufactured are of the type A, U, A. Given these signals, what is the state? at the third unit time. Then what is the probability that in the next time the state of the machine is 1? That is, the machine will be in good state. Similarly, what is the probability that in the next time unit, the next item that is being manufactured would be acceptable? Look at, these are the one which we will be very interested in. Okay, suppose you are being manufacturing some quantities and we have got a string of acceptable, unacceptable and all you are coming. Okay, you would like to know whether you have to stop the manufacturing process or continue. If there is more unacceptable or defective items that are going to come out of the assembly line, you are going to lose money. Okay, so should we continue manufacturing or stop? How do we figure it out? Only by looking at the signals, which are the nature of the items which have come so far. At the same time, stopping the manufacturing is also not good, in the sense that you may potentially lose the profit that you may gain by manufacturing. So it's a question, okay, that can be answered probabilistically. That is what precisely we are looking at. So remember that we will try to formalize the problem. So we have got a signal vector S3 consisting of 3 signals present in obtained from the time 1, 2 and 3. They are A, U and A. So the signal vector is available. As we mentioned, we would always be tracking of this quantity capital F N J, where J stands for the state and N stands for the time. So what it means is, when N is equal to 1 at the first time instant, you would like to know whether what will be F1 of 1, F1 of 2. That is, probability that it produced an acceptable item from state 1, or what is the probability that it produced an acceptable item from state 2. That is what we will call it as F11 and F12. Once we have that one, then we will go ahead and then find out what is F21, F22, because if we are at the second time, the state can be 1 or 2. So this is what we will find out. Both these quantities are needed if you want to go ahead to the next time point and then find out F31 and F32. So we have to keep track of these F's at every time point for all states in order to proceed forward and go up to the state 3, wherein all signals that we have received has been made use of. Then we can predict the future. That is what we will see. So to find out F11 is rather easy. What does it indicate? It indicates the probability, the combined probability of the machine being in the state 1, that is a good state, and the item being manufactured is acceptable. See, always this is given and we have to take this one. There is no choice that you can think of the item being manufactured is unacceptable in state 1 or in the first time. That hasn't happened. Okay, so this is known and we have to use it. So that is why this, although this is not written here, we could have written F1 of 1 comma A, state 1 acceptable, but that is not required because from it's acceptable as given by this string. So there is no need for explicitly writing it. There are only 2 quantities we have to find out in the first time, 2 probabilities, F11 and F12. In the first time, whether it is in a good state or in the bad state, the item being manufactured is acceptable. That is known or given. So what is F11? That is the probability that The machine is in the state 1 and it produced a good item. So the probability that the machine is in a good state to begin with is given to us, which is 0.8. And the probability that it will produce a acceptable item from the state 1 or a good state is also given. Probability of A given 1 producing an acceptable item in the good state is 0.99. So F11 is given by the product of 0.8 and 0.99, which is 0.792. Now coming to F12, the question is the probability that you are in a bad state but produced an acceptable items. Probability of being in the bad state at the first time is 1 minus 0.8 or 0.2, and probability of producing a good item, acceptable item from the state 2 is given as 0.96. So it is the product of 0.2 and 0.96 which is given here. So now we proceed to the second time and so on. For that we have to make use of this formula. Look, at the nth time what do? We compute two things. One is this quantity and another is this summation. So what is this quantity? This is probability of Sn given J. What does it mean? You have to look at the signal that is produced at the nth time. That is, in the second time, where is it? It's better, yeah, it's here only. The signals are given here. So in the second time, if it is unacceptable, you have to only use, for the case of n is equal to 2, we have to use S2 is given as U. And J can be 1 or 2. You may be in good state or bad state. So if you want to find F2 of 1, then you have to use P of U given 1. That will be this factor. If you are calculating F2 of 2, in second time, bad state means it is probability of unacceptable in 2. So both quantities can be taken from this. So this quantity is fixed. There are many terms for all these, this quantity is same. And what we are trying to do is, we are trying to figure out in the second time, what is the probability that you will be, for let us say for J is equal to 1 if you want to compute, we are asking in this question that in the time 2, what is the probability that you are in the state 1 and produced an unacceptable 1. So if you want to be in state 1 in time 2, there are two ways it can happen. You can be in state 1 and remain in state 1. You can be in state 1 in the time 1 and remain in state 1 in the time 2. Or you can be in state 2 at the time 1 and make a transition from 2 to 1. That is the other way. So these are the two ways it can do it. So if you are in state 1 and produced an acceptable quantity in state 1, because that again is known, okay, then that is called, will be given by F1 of 1 or F1 of 2. So these are the two possible things which we have to take it from what we have calculated here. And these are the transition probabilities which can be found out from the Markov chain. So let's do it. F21. So in F21, what is it? You are coming to the state 1. Okay. So you can do that by 1-1 transition or 2-1 transitions. These are the only two ways. And having come to 1, producing a unacceptable item is what we have to find out. That is what PU given 1. So because you are in 1, so this is U given 1. That is the factor that you have to multiply. So find out U given 1 is 0.01. So this 0.01, this factor is common. Then there are two things that you add up in sigma. Sigma over I equal to 1 comma 2. So this is 1, this is 2. So this is what is F1 of 1 times P11. What is F1 of 1 is 0.792 into P11 is 0.9, that is this factor, else it is F12 and P21. F12 is given here 0.192, that you are in a bad state at the time 1 and made a transition 2 to 1, P21. So P21 is 0 because once you are in bad state, it is like an absorbing state, you cannot come back. So that is 0. So this is what you do on multiplying, get this. And next is F22. Well, now don't do one mistake that you can, don't think that you can get F22 by subtracting F21 from 1. F22 is not 1 minus F21. Okay, so that is not right. Well, F22 is what? That is, you are in state 2 at the time 2, and what is the, how is the item that is manufactured? That is given, unacceptable. So here we put unacceptable given 2, which is given here 0.04. So that is the factor that we have to put here. And what are these two factors? That is, to come to 2 at the second time, from 1 to 2 you can make, or 2 to 2 you can make. Okay. So 1 to 2, so being in that is F11 is 0.792, and then 1 to 2 is 0.1, and here F12, the F12 here, n is equal to 2, so if it is 1 to 0.192 into this is actually 2, which is 1. So after computation you will get this. So you have progressed to time 2. So what we have been doing is, we are computing F values for all states for all time, and we keep progressing in time. So now you have to complete it for 3. Again 3. So 3 will have a factor like this one. What will be this factor? That is the first thing you have to look. So you are asking about being in a good state at the third time and producing an item as given by the signal. The signal has given that it is an acceptable one. So what you have to do is, probability of acceptable given 1 is the only thing that we have to put it here. Acceptable given 1 is 0.99. So that is what has to be put. Whereas for the 2, it will be acceptable given 2. That is what will come here. So these two are easily can be figured out. If 1 is the state we are asking, then you have to accept, and you look at the nature of the item here, and based on that you include these factors. And what is the one that is in the bracket? It is, now you have to use from 2 to 3. That is, the, if you are in 2, if you are in state 1 in time 2, and then make a transition from 1 to 1 itself, then you have to multiply this with P11. So this quantity with P11, which is 0.9. Okay, so you get that one. On the other hand, this is and what is the other one? From 2 to 1, the next there will be one more factor, 2 to 1, but 2 to 1 is 0. That is why the other factor is multiplied by 0. You are not writing it. What is F32? That is, this is the acceptable given 2, into f21 times 1 2 sorry f21 into 1 2 1 2 is 0.1 and f22 into p22 of remaining into, that is 1. Therefore, this is the same factor. So you have got it. So you have got all f's. Now what do we do? Now we will answer the first question. That is, the question is, what is the probability that you are in state 3, sorry, in the third time you are in state 1, that is a good state, okay, and produced the signals as given by the signal vector. Of course, you produced an acceptable signal in the third time, so S3 is equal to A. So that when you produced an acceptable item in the third time, what is the probability that you were in state 1 or good state? That is, the question is probability of x3 equal to 1 given s3 is equal to A. So this is P of A given B is equal to P of A intersection B by P of B. That is x3 equal to 1 comma s3 equal to A. And that probability is what we have been calling it as f31. f31 is a combined probability of the last state being occupied and the signals being issued so far. So that is f31. So that is given by this. Divided by what? Probability of S3 equal to A. What is the probability S3 equal to A? See, we have found out in that you could have produced an acceptable item from state 1 or an acceptable item from state 2 with these probabilities. The probability that you produced an acceptable item is summing up the two possible states from which you could have produced it. So you have to simply add these two. That is f31 and f32. If you add up, you are adding over all states. So what is left out is the signal probability of the corresponding signal being issued as given. So you are just adding these two. So you get this value. So we have figured out this conditional probability. Next is the question of to compute x4 equal to 1 given S3. Given that the three signals being produced is given as A, U, A, acceptable, unacceptable, acceptable. Okay. What is the probability that you will go to a good state in the next time? Probability that x4 equal to 1 given the signals. So we can write it as the following. We can introduce the state in the third time as a given state, that is condition it by the state being occupied at the third time and then uncondition it. There are two possible states that can be occupied in the third time. We use that as the condition. That is, this we introduce x3 equal to I, where I can be 1 or 2, and then uncondition is. Probability that x4 equal to 1, here there is only one condition on S3. But now you can put x3 is equal to 1 or x3 equal to 2. There are two possible things, we will put it. But once you put this one, okay, then you have to multiply it by this factor. So if you also put the condition x3 equal to 1, then you have to multiply it by probability that x3 equal to 1 given S3 by the chain rule. Similarly, if you introduce x3 equal to 2, you have to multiply it by probability x3 equal to 2 given S3. So essentially, if you add these two, x3 equal to 1 or 2, both will go away. So you will get this. Now, what is this one? Probability x4 equal to 1 given S3 equal to 1, comma S3, and so on. Okay. Well, you know that once you know the state at the third time, the state at the fourth time is given by the transition probability. Signal will have no more role in that one. So that is given by P11, 1 transition. And what is this quantity? S3 equal to 1 given S3, and that is what we figured out here. So that is not directly obtainable from F's, you have to find this one. So this is what we have got as 0.364. And similarly, if you look at this term, x3 equal to 2 given S3, that is simply given by 1 minus 0.364, because by using all the signals that are issued so far, we are predicting whether S3 is equal to 1 or S3 equal to 2. If the probability that x3 equal to 1 is this one, probability that x3 equal to 2 for the same condition on signals has to be 1 minus that, because there are only 2 possible states. So this is true. You can just 1 minus 0.364 with this one. Okay, this factor is nothing but the transition probability P11, which is P11, and this factor is P221. So P11, from that you will be able to find out. P221 is 0, so we can find out this from the transition probabilities. And at last we also ask the question, what is the probability that the signal that will be issued in the fourth time will be an acceptable item? Probability that S4 equal to A given S3. Okay. So probability that x4 equal to A is what we have to find, but for that these signals cannot help you directly, because they are S1, S2, S3, they don't form a Markov process. But if you know about the state, then we can tell about the probability of producing an acceptable or unacceptable item. So what we can do is, probability of S4 equal to A given x4 equal to 1 is known, because in fourth time, if you are in good state, the probability of producing an acceptable one can be figured out. So we have to make use of it. So we use that fact that in fourth time there can be in 2 possible states, 1 or 2, corresponding probabilities we invoke. So this we write it as S4 equal to A given x4 equal to 1 comma S3 into probability of x4 equal to 1 comma S3 into this quantity S4 equal to A given x4 equal to 2 comma S3 into this one. Okay. Well, I think this has to be a conditional one. Yeah. So we will see that this one, S4 equal to A given x4 equal to 1 is probability of producing a good acceptable item in state 1. That is all given to us. Okay. That's all given to us here. We will make use of it. So acceptable item in state 1 is 0.99, in state 2 is 0.96. So this is 0.99, this is 0.96. And these are obtained from this one, and 1 minus this. So this is how we can solve the hidden Markov chain model and answer some of the important questions that are likely to be asked in any given problem. Next, what we will do is we will take one more example and look at how the time reversible Markov chain formalism can be made use of to answer some of the questions that you may encounter in physics. Although the connection will not be obvious, we will see that you can go ahead and even model such quantities, thermodynamical systems, and draw some very fundamental principles by using the time reversible Markov chain modeling. So this problem has been posed by Ernst. is about how a gas reaches an equilibrium condition when they are allowed to mix. So you have got a gas that is with molecules of the identical kind, and then what we have is totally there are m molecules being present. The volume is being conceptually divided into two, and then what we do is we assume that, and of course we can also have a physical division of this one with only a small hole through which there can be a diffusion, which means that molecules can go between one side of the partition to another side. We can assume that the hole is so small that only one molecule can go in a unit time step, which can be a very small time step, say a nanosecond or whatever it is, appropriate time step. So what we do is, if this is how we assume that mixing of the molecule, the gas takes place, we will look at it from the Markov chain point of view. That is, we assume that one side of the partition we have got I molecules. Totally there are m molecules, so the other side there are m minus I particles. Okay? And then at any given time a molecule can go from one partition to another or vice versa. So we will assume that all particles will be in all possible random state. So those particles which are moving to in this direction will not go through this hole. Only those particles which happen to be going in the direction of the hole, okay, will then cross the boundary and go to the other one. So that is the same, identical for all the particles, and therefore, and there may be a probability that will govern the probability that a randomly selected molecule in the partition will do this crossover, which we do not know, but that if we do not know, but we can only tell that the probability that there will be one crossover of one molecule will be proportional to the number of molecules on this side, because all molecules behave identically. So if there are I molecules, the probability that one molecule crossover, okay, will be proportional to I. Similarly, on the other hand, a probability that there will be a crossover of a molecule in a unit time from the partition containing m minus I to I is proportional to m minus I. Okay. So if you take the state of the system to be the number of molecules in a particular partition and call it as I, then this I is the state variable and which can be looked upon in every discrete time point, and it will range from 0 to m. So it is a discrete state process and discrete time process, and we assume that there is a probability of making a transition from I to I plus 1 or I minus 1, because in every unit time we assume that only one molecule can make a change. Okay, that's a birth-death process. Further, in the next time step, what will happen, which way the molecule will go or may not go or whatever it is, that one is independent of what happened previously, and therefore we invoke the Markov chain property. So it is very similar to a Markov chain of this kind. So it can be 0, 1, 2 up to m, but in each state the probability that the quantity I increases by 1 or decreases by 1 is state dependent. So at ith state, alpha I is the probability that it will go from I to I plus 1. 1 minus alpha I is the probability that it will go from alpha I to I minus 1. And for this model, how do we figure out alpha I? It's like this. This is based on the physical reasoning by understanding the problem. So probability I plus 1 is what we called as alpha I is m minus I by m. and I minus 1 is 1 minus alpha I, which is I by m. That is, from ith the container having I molecules, it decreases by 1, that depends upon I, is proportional to I, so it is I by m. Increases means that depends upon the number of molecules on the other side, that is why it is m minus I by m. Why are you dividing by m? Because then only the probabilities add up to 1. We assume that always one molecule will go this way or that, they don't remain. Okay, if you want we can also model that into, take it into this model. So this is what we have got. This is the time reversible Markov chain, because this is a birth death process and it's always time reversible. We solved it in the previous lecture, and then we got that pi I, probability of occupying the state I at the stationarity, is given by alpha I minus 1 all the way to alpha naught divided by 1 minus alpha I to 1 minus alpha 1. Okay, times pi naught. So if you are in pi I here, assume that this is pi I. So what you have to do is, you have to multiply from here, you have to go here. For that, what are you doing? You are multiplying all these probabilities, and these are the one which work against being here. That is why they are put in the denominator. So alpha 0 into alpha 1, alpha 2 to alpha I minus 1, that is what is in the numerator. And what is in the denominator? 1 minus alpha I, this factor. 1 minus alpha I minus 1, all the way up to 1 minus alpha 1. So that is how we have got this one. Okay, now you can plug it in. So if you put for these factors on the numerator and these factor on the denominator, we will see that the number of terms are same. All of them have got by m on the numerator and denominator. This m will get cancelled with this m. That is one thing which is very clear. And other than that, the first term will be m minus, suppose if it is j, it is m minus j minus 1 all the way to m naught. And here it is 1 minus m1 all the way to this one. 1 minus I, sorry, and so on. So you will have m minus m minus of j minus 1, which is m minus j plus 1, all the way up to m. That will be present here when I is equal to 0. See, when I is equal to 0, it is and the numerator is m. That is why this m comes. And here they are all just these things, I factors, which are j minus 1 to 1. So this is for a general j, pi j. So sigma j varying from 1 to m pi j plus pi naught should be equal to 1. Okay, so this is the, of course we have taken out pi naught. All these will also have pi naught. The pi naught here and these pi naughts have been taken out, and they will add up to 1, and therefore pi naught is the square bracket power minus 1. So again we can absorb it here and then write it as j vary from 0 to m and so on, and that can be found out to be, it is nothing but, you will see that this will be an expansion of sigma j varying from 0 to m mj. Okay, it is actually what happens into 1, it is actually some expansion for 1 plus 1 power m, then only these things will come. Okay, 1 by 2 plus 1 by 2 power to power m. If you expand it, you will get this one, and the constant factor of 1 by 2 will be there. Okay, so that is what basically comes out here. So how did we get it? If you take n by 2 plus 1 by 2 power m, you get this one, that is 1. So you get this, So this is nothing but the expansion this. So if you take this factor, okay, this and this are this inverse. That is how you got this one. So what basically it tells is the state probabilities have this distribution, which is a binomial distribution. That is the probability that there are I molecules in a given on one side is as a binomial distribution. So which means that it is the probability that a given molecule is on one side, and then if you add that probability of all molecules, you have got a binomial distribution. Which means that the probability that a particular molecule is in one side or other has to be a Bernoulli process, because only a summation of a Bernoulli process leads to a binomial distribution. So it is clear that the probability of a given molecule occupying one side or other is a Bernoulli process with a probability 1/2 on one side, 1/2 on other side, which means that it is equally likely to be in either one of the wall. Okay, so this is how the equilibrium is being reached. So we have of course arrived at something which is a very intuitive one, but using our well-known mathematical formulation of the discrete time Markov chain. Thank you.